Okay, thank you. Good afternoon, everyone. So I'm Claudio Gomes. I'm here to present ongoing work on trying to build reusable and reliable digital twins. And the approach in general is trying to deconstruct these things, trying to identify what are the building blocks of digital twins, and then help you, using those building blocks, help you build, reconstruct digital twins that are more reliable. This work has started in the RoboSAPIENS project, but also evolved in this DigitBench project where we built, a digital twin of one of these wind turbine nacelle testing systems. So it's very big. You can see a person down there, but this tests the wind turbine end to end. So allows you to test the integration of the different components. And of course, there's different companies involved. There's a power system company. There's the supplier of the nacelle, etc., and they need to collaborate together to even set up these tests. But during my explanation, I'll use a much simpler system because otherwise it's kind of hard to follow. So an incubator system that tries to maintain the heat inside a volume. Very simple. Think of an oven, for example. That's a form of incubator. And our digital twin, what is it? Well, it's something that lives in the cloud, right? It gets data from the system and provides a few services to a user, such as, a nice dashboard showing the history of temperatures. It can provide monitoring to detect that whatever your incubator is not undergoing any dangerous temperature fluctuation, for example. And I'll focus on one particular service, which has to do with tuning the controller. So tuning the component that decides when to turn on the heater and off the heater. It's a very simple component. And this is how that service looks like, right? The user will occasionally go and open the lid of the box, so like opening the lid of your oven, for example, which will then make the heat escape, right? So the temperature will drop, and maybe the oven you have at home, if it's not one of those smart connected ovens, will likely simply use more energy to try and warm up your house instead of the contents of the oven, right? Which is not very smart. And then, of course, you close the oven, and now you have a lot of energy inside the oven, so the temperature can go quite high. If you're trying to cook something, you'll just roast it. So what we want is to use a model, right? To use a model of what's happening inside the oven to detect that that you've sorry, just keeping track of time, that you're trying to detect that the lid has been open, and then you adjust the controller to recognize that since the lid is open, don't use as much energy. That's a simple feature. You could, of course, train a reinforcement learn agent to do this, right? So it's not a particular complex example. I would like to show more or less from a systematic point of view what are the reusable components in this setup from a digital twin point of view, and then discuss a bit what are the challenges to make those components reliable. How can we really argue for their correctness in an operating sense in general. So at first, these are the main components I have. I have the physical twin, which is the plant and the controller. The plant is the oven itself, the air volume, the heater, etc. I have the controller, which is a state machine running on a Raspberry Pi, something simple. And then I have an observer. So this will actually gather the sensor data, the measurements of the temperature, and try and maintain an up-to-date state of the full oven. That means the temperature of the air, the temperature is being read by the sensors, etc. Think about things like a Kalman filter that's being done here, or a sensor fusion component, or even a neural network could do that. And then I have a digital shadow. What this is doing is effectively when you open the lid, you're effectively changing the operation mode of the system. So you're changing the system dynamics. You're no longer considering the plant as being the air volume inside the oven, but actually the air volume in the room where the oven is. So this changes, and this digital shadow is trying to maintain an updated model of the plant. And that means, for example, updating the parameters of a differential equation that describes the temperature dynamics inside the air volume, right? Since the air volume changed, then the dynamics change. That's what the digital shadow is doing. And then I have this energy saver, which is really updating the controller whenever the system operation mode changes. And these are, so you get the sensor data being sent to the observer. The observer outputs the state and as well as some estimation error, some kind of uncertainty. The digital shadow effectively outputs a history of the parameters or the models that were used to describe the plant as well as the current state. And this energy saver effectively tries to run an optimization loop to try and see what is the best control parameters at the moment to then optimize the controller here. And this is a very general system, right? So you can see this kind of loops in effectively, this is very similar to a MAPK loop, right? So every time a system you want to make it self-adaptive, you have this kind of these types of components. So building our way backwards from the energy saver and trying to describe what is going on inside of them, what we see is well, it receives a plant model and state and should produce some controllers, some control parameters, but it's effectively using a design space exploration loop. So, which means it's an optimization problem, trying to find the minimal parameters, and the cost function typically involves running multiple simulations under different scenarios and calculating some fitness over those simulation traces. The key part here is that these simulations are using the current model, the current model of the system, right? So it's using the current controller. It's using the best model of the plant so far, the most up-to-date model of the plant, coupled with the model of the controller under different parameters. Right, so we are manipulating in this system. We're kind of manipulating and plugging in these different models together to run different simulations. And these simulations typically start from the current system state. It go into the future, trying out different possible futures, and then evaluating a cost on each of them, and then finding the minimum among those. So that is what a very general controller tuning service does. If you going backwards with the digital shadow, what it's trying to do is checking whether the estimates being given by the system observer, if the uncertainty is too large for some period of time, right? You can decide how to measure this. But if these uncertainties accumulate over time and are growing, then you would probably start a new identification process to find a new model for the system operation mode, right? So you try this could be training a new neural network to fit the new system dynamics, but it could also be finding new parameters for a differential equation, and that gives you the new model, right? And this is well known as well. There's a field for it, right? System identification. Training of neural networks, they all try to accomplish a similar goal. Now, the plant observer, if you've seen Kalman filters, you get a gist of what this does, but it's effectively running two steps. First one is runs a simulation of the current system dynamics. So effectively obtains a prediction of the state of the system, and then performs a correction where it corrects this prediction as a function of the sensor data that was obtained, right? Which may not be necessarily representing the full system state, right? So there's two parts. There's the system measurements and the system state. And typically the system state includes the system measurements. And then does a correction and estimates the uncertainty. So it looks at the previous uncertainty, previous states, computes a new state and new uncertainty. That's how usually observers work. And you can also train neural networks to do this observation step, to receive sensor data and predict the system state. So these things, when they're put together, right, each of them is fairly general. There are many different algorithms to accomplish each of these components, but they give you quite some power in developing a system that is self-adaptive, that can react. This would react, this loop, the software loop which we've developed for an incubator, it reacts not only when you open the lid, but also when you decide to put a bucket of ice inside the oven, right? As long as you have a nice defined fitness function for the controller tuning, the system should learn how to best carry out its function, right? And we also, of course, because we're in Denmark, we also fermented beer using this kind of approach, right? So we could do lagers, we could do the other types of beer. But these are the core components, right? This simulation, simulators, state estimators, system identification loops, right? More simulators, but combining the models in different ways to run simulation, right? Having a standardized access to models and model coupling, right? And also, of course, optimization processes, design space exploration. So these are the core components of digital twins. That's my argument, right? And if, I'm going to skip these details in the interest of time, but I'll be in the coffee break. We can discuss this if you have any questions there. This is just giving some details of these different components, but essentially digital twin composition is composition of these building blocks. If you want to evolve, if you want to compose this digital twin with other digital twins, my argument is that you should do it at the building block level, right? These are the Lego bricks to build your systems. And there are ways that here they're combined in a very simple scripting language. I'm using if-thens, and so on. But there's been work in the state of the art that are trying to use languages that are where these components are first-class citizens and they have a well-defined type, and then using type checking and formal verification, you can check if these things are being correctly combined, if you're using this in a correct way. But there's way too much work to be done in this area. Now, going into reliability, the challenge here is at the moment we understand very well models. If you go to an engineer like Roland, for example, there's very good processes to understand when are models a good predictor of what's going on, right? But for example, if you look at model observers, state estimators, Kalman filters, which are using models, we don't understand so well under which conditions they work, right? This is not so well understood. And if you train a neural network to play as a model observer, you also need to, the extensive experimental methodology, you need to prove that it works in these conditions. It would be nice if we could, understanding the models would be enough to get a good understanding of model observers. Same thing, planners, these kinds of, the controller tuning approach, does it always respect the model's operational envelope or not, right? So these are the kinds of things we need to reason about. And there are other loops like system identification, for example, the process of exploring these different scenarios with the model to estimate its parameters. You also need to generate scenarios that are persistently exciting so that you don't end up in a situation where there are parameters which are not correctly identified. You recognize this problem in machine learning as well, having a data set that's quality, that's good enough. My argument is that we should be using contract-based design, right? So we should have components like the models, the simulators, so these core building blocks of digital twins. They should come with contracts. We should have things, for example, the model says the model can monitor its own inputs, the way you're using the model, and can assuming that the inputs are within the operational envelope of this model, can give you a guarantee of how much prediction error you're getting. Right? And then you can plug these guarantees provided by the model. You can then plug them into the simulator, and you create a new component with a new contract that you can then get guarantees of, right? And so on and so forth. The state estimator uses a simulator, so it will also get guarantees by propagation, by transitive propagation of these assumed guarantee contracts from the other components. This is just one axis of these contracts, there's stability. You've heard of stability in systems. There's a timing, of course. For example, a model that has a particular complexity for evaluation of derivatives will translate to a particular complexity when you're running simulations of a model, right? And so on and so forth. There's not enough time to cover these, and these are by no means complete taxonomy of the contracts that are there. But sometimes each of these contracts there's a whole research field trying to understand what these are for that component. So there's quite a bit of work to do. And these are examples in the slides, which I think will be made public of contracts that have been that we've elicited for different components of digital twins. That's me. Yeah, as I said, I'll be outside if you have any questions to discuss this further. Thank you.